So let us go to the next speaker. Next speaker is Vaishak Prasad. He will be talking about tidal deformations of dynamical horizons of binary black hole mergers. So Vaishak, could you please share your screen, your slide?
Hello. Yes, am I audible?
Yes, we can hear you.
Yeah. Let me share my screen.
So I will try to switch on my video and show you when it is 12 minutes. Okay, so time to time you.
Yeah, could you please interrupt me once at 8 minutes?
Okay, sure.
Okay.
Okay, please.
Visible as well?
We can see your slide.
Okay. First of all, I would like to thank the organizers for giving me this opportunity to speak. I'm Vaishak Prasad. I'm finally a PhD student working under Professor Sukanta Bose at Ayuka, Pune. Today, I'm going to talk about the tidal deformability of dynamical horizons in binary black hole mergers, a work which I recently completed in collaboration with Anshu Gupta, Sukanta Bose, and Badri Krishnan. So this work is based on the following article, which is going to appear in Physical Review D soon. So what I'm going to do in this talk is to introduce the idea of tidal deformations and explain why it's important to study them, noting the limitations of existing treatments to black holes especially. And then I'm going to explain the alternative approach that we have taken in this work, namely to study the tidal deformations of black holes using dynamical horizons. And I'm going to give more details about the numerical simulations that we carried out to achieve this, and I will discuss the results. So the physical system is as follows. We have two compact objects, in this case, black holes, which are orbiting each other and merging. In the process, they are emitting gravitational waves. The question is, how does one understand or find out the deformations of black holes in this process, and also their effects on the emitted gravitational waves. So tidal deformability is a topic which has been studied since the 1800s, in especially the context of tides on black hole, on the oceans, water bodies on Earth. And they were usually treated in this Newtonian methodology. Namely, the source distribution of the compact object which is being discussed is computed and decomposed into a multipolar distribution, which is called QL here. And the external tidal field, which is disturbing this compact object, is labeled as epsilon L, which is also decomposed in multipole moments. And then one can show that the change in the multipolar distribution of the source is proportional to the applied external tidal field, and the constant of proportionality is called a love number. This is the Newtonian story. In the relativistic treatment, however, especially in the context of black holes, there are two deformations that appear. One is called as a mass multipolar deformation, and the other known as the current multipolar deformation or the spin multipolar deformation. And it is convenient to use the multipole moments of the gravitational field far away from the system, called the Garrosh-Hansen multipole moments, decompose the metric into a background and a perturbative part, which is further segregated into an external part, which is exclusively due to the external tidal field applied, and a small part, which is basically the response of the source to the external perturbations introduced by the tidal field. And thus here, the multipole moments of the object, the Garrosh-Hansen multipole moments, change because of this response, and a similar constant of proportionality can be shown to hold, thereby defining the love numbers. So there are various, there is a lot of work that has happened to study tidal deformations of black holes. And they all either use the perturbation approach, which I discussed now, or some of them discuss the tidal deformations of compact objects which have a source distribution like neutron stars, and take the limit of compactness of a black hole to derive the tidal deformations of black holes. And most of these works tell us that the tidal deformations of non-spinning black holes are zero. Now, some of the limitations are that all of these are discussed in the context of static tides. And the tidal deformation of the compact object or the black hole is only assumed to have a parametric dependence on time because of the proposed, the assumed slow kind of evolution of the tidal field. The tidal field is assumed to be weak, and therefore one needs to have access to the asymptotic regions of each black holes. However, in practice, in a binary black hole merger, most of these assumptions cease to hold, especially when the black holes come close to each other. One cannot isolate the asymptotic fields of each black hole. They are strong and they are highly dynamical. So black hole perturbation theory is not the right tool to understand the tidal deformations of black holes in this context. So what we have attempted to do here is to address the same question using what are known as dynamical horizons. So on the left-hand side, there's a Penrose diagram of a Vaidya spacetime. There is a Minkowski region, which is shaded in orange. There is shortly thereafter collapse of null dust, which causes the formation of trap surfaces, which is trap regions, which is shaded in black, in gray. And therefore, at late times, as the null dust ceases to collapse, there is a black hole formed, and there is an event horizon labeled by E+. As you can see, the location of this event horizon can only be found if one knows the evolution of the space-time infinitely into the future. And therefore, even flat regions of space-time might as well be developing an event horizon. Therefore, because of these unfavorable teleological properties of these event horizon, it is more convenient and easier to study the dynamics of black holes in such dynamical scenarios using what are known as dynamical horizons. These dynamical horizons are surfaces where the expansion of the outwards going null vectors vanishes. And this is usually a space-like hypersurface, three-dimensional hypersurface. Its cross-sections are closed spheres in general relativity, and they can be used to represent instantaneous horizons of black holes, for example, in a numerical relativity simulation. So these dynamical horizons have been extensively studied and established, starting with, in fact, Penrose, which he used in tackling problems related to singularities. And they have been used to understand dynamical black holes by Hayward, Ashtaker, Krishnan, and a lot of physics and their mathematical properties have been studied, which I will not dwell into. The most important point to note is that the expansion of the outward null vectors vanishes. So in this work, what we attempt to do is to understand the tidal deformation of the horizons of black holes using their source multipole moments in contrast to the field multipole moments of Gerosian-Hansen. These source multipole moments are defined as integrals over each leaf of the dynamical horizon S, which I represented here. And they involve an integration of the two-dimensional Ricci scalar of that surface labeled as R tilde here, and they are integrals which go right over the surface. And these represent the geometry of the horizon. So for example, the M0, which is the n equal to 0 multipole moment, is the mass of the black hole. And in the absence of an external tidal environment, for a non-spinning black hole, all the other multipole moments are 0. Whereas in a numerical simulation, when a black hole is under the influence of its companion, these multipole moments evolve with time, and those multipole moments which were vanishing when they were isolated no longer vanish, and they have finite values indicating the extent of the deformation of the black holes.
So Vaishak, you have taken 9 minutes.
Thank you. So what we did to quantify the tidal deformation of black holes is to expand the change in these multipole moments, which happen due to a deformation in the horizon geometry, in a Taylor-like expansion involving the parameters of the system. And therefore, the coefficients alpha ij, which are pre-multiplying these system parameters, are dimensionless, and also they are independent of the parameters of the system, and therefore they must be universal. They must characterize the tidal deformations of all black holes, independent of their masses. In this work, we are only considering non-spinning black holes, so we do not take into account effects coming due to spin here, although this expansion can be augmented to address those questions as well. So in this expansion, the leading order term is expected to come from 1 by dq, and that is because of our Newtonian expectation. And we have two models, one at the Newtonian order, which appears as 1 by dq, and the second, which involves one more extra term, 1 by d power 4. And what we are going to do in this, what we did in this work, is to run numerical simulations of binary black hole mergers, track the apparent horizons, the foliations of the dynamical horizons, compute the source multipole moments, and study their evolution with respect to time and distance, and in turn use fitting to estimate these dimensionless coefficients, alpha 1, 2, alpha 2, 1, etc., and try and see how they behave in the due process of merger. So we use the Einstein toolkit, the publicly available numerical relativity code, and various numerical simulations were run with mass ratios ranging from 0.4 to 1, which the parameters of which are listed in this table. And now I turn to the results. So on your screen, you can see on the left-hand side, the first figure on the left, the multipole moment of black hole 1 for one of the numerical simulations for q equal to 0.4, plotted on a logarithmic scale with respect to distance. The data is plotted in black, and the two models that we use for fitting, model A, which dealt with Newtonian order, and model B, which also included one higher order term, 1 by d power 4 term, are shown here, the fits of those models to the data. And on the right hand side, we see the same for black hole 2. So as you can see, the model, the Taylor-like expansion models very well describe the evolution of the multipole moments in a binary black hole merger. Especially model B, which involves a 1 by d power 4 term, is shown to be more important in the evolution of the multipole moment as the distance decreases. The distance decreases as the black holes merge.
So Vaishak, it will be good if you can go very fast within 30 seconds or so.
I'm done. So here are the tidal coefficients that we obtained. So we could estimate 5 tidal coefficients. And I will conclude now by leaving you at this slide. And most importantly, these love numbers are computed using the source multipole moments, which may be more important to understand the deformability of black holes, especially when they are close to each other, and may have important implications for the tests of no-hair theorem, for example. In future, we would like to also explore the observational implications of these results. Thank you. Thank you for your time.
Thanks, Vaishak, and thanks for excellent timekeeping. So I see only one hand so far now. Amitabh, please go ahead.
Okay, and thanks, Manjri. And thanks, Vaishak, for the nice talk. Actually, I would like to understand the definition that you have a little bit more. So you have this integral over, this definition. So the R tilde is the Ricci scalar of the surface S, and Pn are the Legendre polynomial. Is that right? You did not say.
That's right. Yeah.
Okay. Okay. So now my question is, what is this S? Actually, what I did not understand is what is this S?
So S is in just indicating that one is integrating over the two-dimensional slices labeled here as S0, S1, so on.
Yeah, but if I look at the left-hand side figure, you have a space-like surface. So how are these S's constructed?
So the right-hand side also shows space-like, the right-hand side is also a space-like hypersurface. It's only null after S1. After the null dust ceases to collapse, at this point, the horizon is isolated. So below S1, the horizon is dynamical and is space-like.
Oh.
Sorry, does that answer your question?
Yeah. So, okay. I see. So any topologically spherical surface would do, I guess.
So these surfaces are found in a numerical simulation which incorporate these conditions that the expansion of the outgoing null normal vanishes, and they are topologically spheres.
Okay.
They can be deformed spheres, but topologically they are spheres.
Okay, thanks.
And Jerry, I noticed there is one more question. I think
and he already promised me that it is a quick question.
Okay.
Yeah, so I'll just ask it. Hi, Vaishak. So my question was, I'm not very familiar with these kind of things, but I was just wondering from the observational standpoint, what are we missing in the current waveform models that can be accounted for? So in your last slide, you had something like observational implications, but what could be the observational implications?
Yeah, thanks for your questions, Aditya. This is exactly what we are trying to understand now. And yeah, I wish I could tell you something concrete, but as of now, I'm also at the same stage where we are trying to understand what could be important effects of tidal deformations in the latent spiral merger phase. We could discuss sometime.
I see. So will there be a large phasing issue? Will the phase differ by a lot?
Yes. So yeah, so there are possibilities of that happening, and I'm not very confident on these things. So well, as the horizons get deformed, the flux of energy momentum would also changing some of the balance laws. But I'm sorry, I won't be able to give you any concrete results on phasing yet. We are not sure about it.
Okay, thank you.
We could discuss sometime. Yeah.
Thanks, Vaishak. So there is one question in the chat message. Probably you can later reply to Sajat. So we can go to the next talk. Next talk